Hello, we'd like to work through forces two-dimensional equilibrium problem here. So we have a 15-kilogram ham hanging by two ropes as shown in the diagram. And let's go ahead and start working it. As usual, to start any force problem, we're going to draw a free body diagram. I'm going to claim my positive directions as up and to the right. We have two contact forces, tension 1 and tension 2, pulling upwards. Tension 1 pulls up and to the left, tension 2 pulls up and to the right. And we have weight down, and we have zero acceleration because this is hanging in a static equilibrium. Now, this free body diagram is going to be our map to help us build our correct equations in the x and y directions. So I'm going to start first by writing a Newton's second law equation for the vertical direction. And since it's in equilibrium, there's no acceleration or no net force. So this means all the forces in the y direction will cancel out. And I'm going to walk around my free body diagram here and account for every force. And as I come across a force, I'm going to ask myself, since I'm in the y direction here, is it an up or is it a down thing to get my sign correct? I'm going to ask, is it all or some, to understand if I want to just be including the whole vector or a component of that vector for the vertical direction. And the first force I come to is, I'm going to start right here at T1, and it's up, so I have a positive number, a positive value there, and it's only partially in the vertical direction, so I'm going to indicate that by this little subscript y. This says the vertical component of T1. Next, I come around to tension 2, and it's upwards, so I say positive, and it's only the vertical component of it, so I put a little subscript y, say the vertical component. It's only some of tension 2 is upwards. So I did T1, T2, walk around to my final vector, and that is weight, and it's downwards, so I indicate a negative sign, and I know it's all of it, so I do not include a little subscript here. Now that I know this, I can go in and put some details. This first line is a simple story of what's happening. It says tension 1, only some of it pulls up, plus tension 2, some of it pulling up, counteracts all of the weight down. Now I'm going to go through and put in the details. So for for the vertical component of T1, I need to put in some kind of a trig function here to handicap it and only give part of T1 in that direction. So let's go ahead and work some trig to figure that out. So I'm going to draw T1 here. And here are the vertical and horizontal components and the angle that it's at. And I want to understand how to put in some trig in there to give me just my component, not all of T1. So I'm going to use sine because I want the vertical component relative to this angle and the hypotenuse. And so I write out my sine 60 is opposite over hypotenuse, so sine of 60 is opposite over hypotenuse. And then I can rewrite this in terms of the vertical component. So wherever I see T1y, I can write T1 sine 60 instead. So I'm going to do that right up here. Okay, so let's go ahead and continue doing the details. I'm going to do something similar for T2y. So I need to understand how to write T2y to capture just some of the tension 2 in the vertical direction. So I'm going to write a little vector triangle here again of its components. And I'm going to do something similar that I did up here. I'm going to multiply by a trig function. So I need to get the vertical component, so that's going to be opposite of 30 is my vertical component, and the hypotenuse is over here, so I can do sine 30 is going to be opposite over hypotenuse. Sine 30 is opposite over hypotenuse. And wherever I see T2y, I can write this instead. And I do that right here. And then lastly, I add in some details about weight here. It's mass times gravity is the equation for weight, so I can substitute that in. So I'm going to rewrite one more time just to plug in all my known information here. And I'm going to plug in some values for mg. Alright, so that's all the known information I have for the vertical direction. And we'll notice that we have one equation and two unknowns. So we cannot solve directly. We need another equation to solve. So we're going to get that from the x direction. So let's write out our Newton's second law for equilibrium in the horizontal direction. There's no acceleration or net force, and I'm going to once again just walk my way around this free body diagram to account for all the horizontal forces. I'm going to start with T2, and it pulls to the right, so I have a positive value, and it pulls only partially to the right, not totally to the right, so I'm going to indicate that with a little subscript x here. Next, I come around and I come to weight, and I say, is this a left or right thing? And it's neither, so I skip him and I come over here to tension T1, and it is a left thing, so I indicate that with a negative sign, and it's only partially to the left, so I indicate that with the subscript x, so to say only the horizontal component is acting in the x direction, not all of it. So now I can put in some details. Now I need to do some trig again to indicate just the horizontal component. So we can do something similar that we did last time with the vertical direction. And since for T2 I want the horizontal component that's adjacent to the 30-degree angle, I can write cosine is adjacent over hypotenuse, and I can solve out again for the horizontal component, and it looks really similar to what we did for the vertical direction. So wherever I see T2x, I could write T2 cosine 30 instead. Next, we'll put in the details for T1x. And I'm going to have to do a little bit of trig here also. So T1x, we want to grab the T1x is adjacent to the 60-degree angle, so we can use cosine for this. Cosine is adjacent over hypotenuse. I can solve away for T1x, so wherever we see T1x, I could write T1 cosine 60 instead. So I'm going to do that right there. Now, this equation that we just wrote has two of the very same unknowns we had up here, so now I have two equations with two unknowns and I can solve. I'm going to use substitution to solve away. So I'm going to take this equation and I'm going to isolate for T1 or solve for T1, and wherever I see that up above, I'm going to substitute it in, and then we can solve. So I'm substituting it in right now. I use little brackets to communicate that I did a substitution. And just rewrite. Okay, now this equation, for this one equation, I have just one unknown inside of it, and I can solve away. So basically this is our variable is equal to a number times a number divided by a number. So this is just going to be one big number right here. So our variable times a number plus our variable times a number minus a number. So we should be able to solve that. I'm doing some mathematics. So I do a little bit of math, and we get to solve for T2. It should be equal to 73.5 newtons approximately. Okay, great. Now that we have this, we can solve for T1 by going down here and substituting this value into this equation right here and solving for T1. So I'm going to insert my 73.5 into the bottom equation, and I get an answer of 127 newtons approximately. So now we have our solutions. I just want to take a second and look at how vector addition would work out for something like this. If we add our vectors, so we start with weight down, and then from there we add tension 2, and then from there we add tension 1. Something interesting happens here. Net force just means add the forces, and so we can do vector addition to add those forces. But when we add the forces, net force is equal to 0. So if we start here and we add weight and then T2 and T1, we actually end up at the same place we started at for no resulting force, or net force equals 0. And so that's kind of a nice visual way to think about equilibrium problems, is like when you add all the forces, they add up to 0. And that's a good kind of follow-up for this. And so one last thing to note here is that since T1 is the more vertical of the two forces, it actually supports most of the weight of this thing hanging down. Is another thing to notice. And that's pretty much how you would work an equilibrium problem in 2 dimensions. We first start out always by using a free body diagram. That's going to be our map for building our Newton's law equations. I start out with telling a simple story in the vertical direction by asking and walking around this free body diagram. Each time I came to a force, I asked a simple question of, is it up or down, and is it all or some? And I built a simple expression. And then I put in details. I did the same thing for the horizontal direction. I went to my free body diagram, I walked around this thing, and each time I came to a force here, I would ask myself, is it left or right, all or some? And that allowed me to build a simple expression here. Then you add in the details. We noticed that we had 2 equations, 2 unknowns, and we did some math, some substitution to solve away, and there you go. This is how you do an equilibrium problem in 2 dimensions.